Why does the quantum world refuse to obey the rules of everyday life? That single question has sparked 30 competing theories, each offering a unique window into what reality might truly be. By the end of this journey, you will see that the universe itself may be far stranger and more beautiful than you ever imagined. Could the universe be splitting into countless copies every moment, or is consciousness the force that pins down what we see? What comes to mind when you think about the nature of reality? The most famous answer is also the oldest, and it has shaped how generations of physicists think about the quantum world. This is the Copenhagen interpretation, developed in the 1920s by Niels Bohr and Werner Heisenberg. At its core, the Copenhagen interpretation says that a quantum system does not have a definite state until it is measured. Before measurement, an electron exists in a superposition of all possible states at once, like a spinning coin that is neither heads nor tails while it is in the air. The moment you look at it, the coin falls flat and you see one outcome. That moment of measurement is called wavefunction collapse, and it locks reality into a single classical result. Bohr insisted that the role of the observer was fundamental. He argued that physics should not try to describe an objective reality that exists independently of our experiments. Instead, science should only describe what we can actually measure and observe. This was a deeply pragmatic approach, one that kept the mathematics clean and the predictions accurate. Many physicists adopted a kind of practical motto: shut up and calculate. They stopped worrying about what was really happening and focused on using the equations to get the right answers for experiments and technologies. But for many others, this stance felt incomplete. It left a giant question mark hanging over the nature of reality itself. If the universe only becomes real when we look at it, then what about all the time before humans existed? And what counts as a measurement anyway? Does a conscious mind need to be involved, or is any interaction between particles enough to cause collapse? These unanswered questions pushed some of the brightest minds to search for alternatives, ideas that would give a fuller picture of what lies beneath the equations. One of the most dramatic alternatives came from a young physicist named Hugh Everett in 1957. While still a graduate student at Princeton, Everett proposed a radical answer to the question of wave-function collapse. What if, he asked, the collapse never actually happens? What if every possible outcome of a quantum measurement simply plays out in its own separate branch of reality? Under his interpretation, now called the many worlds interpretation, the universe is constantly splitting. Every time a quantum event occurs, the universe divides into parallel branches, each realizing a different result. The electron is measured as spinning up in one branch and spinning down in another. Both outcomes are equally real, they just exist in different, non-communicating realities. This idea has a kind of elegant simplicity. It removes the need for a mysterious collapse process entirely. The mathematics of quantum mechanics describes all superpositions smoothly, without ever requiring a sudden jump to one definite state. Everett argued that we should take the mathematics literally. If the equations show a superposition, then superposition is what reality actually is. We experience only one branch because our consciousness is tied to that particular path, but all the other branches are just as real. The immediate implication is staggering. There is not just one universe, but an infinite multiverse. Every choice, every random quantum event, every possibility that could happen does happen somewhere. There is a version of you reading this sentence and another version that just closed the video. There are branches where history unfolded differently, where dinosaurs never went extinct, where you were born in a different country. The number of branches grows exponentially with every passing moment. Many physicists find this interpretation appealing because it is mathematically clean and requires no extra mechanisms. It treats the observer as part of the quantum system, not as a special outside agent, but it also raises a troubling question. If these branches are truly separate and never interact, can we ever prove they exist? The interpretation makes no testable predictions that differ from standard quantum mechanics. It explains the world we see by invoking countless worlds we cannot see. Some scientists worry that this makes the theory unfalsifiable, a metaphysical claim rather than a scientific one. Others point out that the very notion of splitting is ambiguous. Does the universe split at every measurement, or does the whole entangled system split all at once? And what defines a measurement anyway? The same problem that haunted Copenhagen reappears, though in a different form. Everett's idea remained on the fringes for decades. It was seen as too strange, almost science-fictional. But over time, as physicists grew frustrated with the unanswered questions of Copenhagen, many worlds gained serious traction. Today it is considered one of the leading interpretations, and it continues to inspire both rigorous research and wild speculation. Yet it is not the only way to banish wave function collapse. Another theory, developed around the same time, also rejects collapse but offers a completely different picture of reality, one that introduces hidden particles guided by a strange quantum potential. That is where we turn next. In 1952, a physicist named David Bohm revived an old idea first proposed by Louis de Broglie more than 2 decades earlier. The core insight was beautifully simple. Particles, like electrons, have definite positions at all times. They travel along precise paths, but each particle is accompanied by a quantum wave, a pilot wave that guides its motion. This wave is not just a probability wave, it is a real physical field that pushes and pulls the particle according to the Schrödinger equation, the same equation used in standard quantum mechanics. The result is a deterministic universe. If you knew the exact position of every particle and the exact shape of its pilot wave, you could predict its future path with certainty. The randomness we observe in experiments is not fundamental. It is only a reflection of our ignorance about the hidden details of the wave and the particle. Under this interpretation, an electron fired at a double slit always goes through one specific slit. It never splits, but the pilot wave passes through both slits, interferes with itself, and then directs the electron to a landing spot on the detector. The pattern that builds up over many electrons matches the famous interference pattern exactly, because the wave determines where each particle lands. Bohm's theory reproduces every statistical prediction of standard quantum mechanics to perfection. It is a complete alternative, not a competing experiment. Yet it makes a deeply unsettling claim. The pilot wave carries information about the entire experimental setup, and it influences the particle instantly across any distance. This is non-locality. What happens to one particle can affect another particle far away, even if no signal could travel between them at the speed of light. Einstein called this spooky action at a distance, and he hated it, but ironically, Bohm's theory fulfilled Einstein's oldest dream. It restored realism. Particles exist and have properties whether or not anyone measures them. The universe is not dependent on an observer. For Einstein, that was essential. Bohm gave him a deterministic universe with real particles moving along real trajectories. The price was non-locality, a connection that binds the entire cosmos together in a single quantum web. Many physicists rejected the theory for exactly this reason. They found it awkward, almost clunky, to have a hidden wave pushing particles around, and the theory has never gained as many followers as Copenhagen or many worlds. Yet it remains a powerful reminder that the mathematics of quantum mechanics can be interpreted in more than one way, and that our intuition about reality may need to stretch further than we ever expected. A different approach rejects both hidden variables and parallel worlds. Instead, it proposes that the wave function collapses on its own, spontaneously, without any observer or conscious mind required. These are the objective collapse theories, and they offer a third path that feels both radical and grounded in physical mechanisms. The most famous example is the Gerardi-Rimini-Weber model, developed in the mid-1980s. Under GRW, every particle has a tiny, random chance of being hit by a spontaneous localization event. Most of the time, nothing happens. The wave function spreads out quietly as the Schrödinger equation dictates. But every so often, completely at random, the wave function of a single particle gets sharply localized, pinned down to a specific region of space. These hits are incredibly rare. For a single electron, you would have to wait about 100 million years for one event to occur. So for all practical purposes, an isolated particle behaves exactly as standard quantum mechanics predicts. But here is the twist. When many particles are bound together into a large object like a baseball or a human being, the collective rate of hits becomes enormous. With trillions upon trillions of particles, a spontaneous localization event happens somewhere in the object almost instantly. That single event localizes only one particle, but because all the particles are entangled with each other through their interactions, the localization effect spreads and the whole object collapses into a definite position. The result is that large objects always appear classical with a well-defined location, while tiny particles can remain in superposition for long periods. This matches what we observe in labs. An electron can be in two places at once, but a baseball never is. The mechanism is built into the physics itself. No observer needed. Another version, proposed by Roger Penrose, links collapse to gravity itself. Penrose argued that when a massive object is placed in a superposition of two different locations, the gravitational field around it also becomes ambiguous, curved in two different ways at once. This creates a fundamental instability. After a very short time, the universe cannot sustain that tension, and the superposition collapses into one definite configuration. The more massive the object, the faster the collapse. For a tiny particle, the effect is negligible. For a grain of dust, the collapse happens in a fraction of a second. For a human, it happens almost instantaneously. This idea elegantly connects the quantum world to Einstein's general relativity, two pillars of physics that have stubbornly refused to merge. What makes these theories especially exciting is that they are testable. Because they predict that collapse is a real physical process, they also predict small deviations from standard quantum mechanics. For example, if you try to put a large molecule into a superposition, objective collapse says the superposition will break down faster than the standard theory expects. Experimentalists are now designing tabletop experiments that push larger and larger objects into quantum states, watching for any hint that the wave function decays on its own. If a deviation is ever measured, it would revolutionize physics. It would mean that collapse is not an abstract mathematical rule, but a real event happening in the world, shaped by gravity or by some yet unknown random field. Until then, these theories remain elegant proposals waiting for a decisive test. They remind us that reality may not need a witness to become real. It might simply happen on its own, one tiny localization at a time. But what if the wave function is not a physical thing at all? That is the radical claim at the heart of QBism, a modern interpretation whose name stands for quantum Bayesianism. The central idea is that the wave function is not a real object floating in space or a field that guides particles. Instead, it is a tool, a mathematical expression of an individual's personal beliefs about what might happen in a measurement. Probabilities become degrees of belief. When you say an electron has a 50% chance of spinning up, you are not describing a property of the electron. You are describing how confident you are, given your knowledge and experience, that you will see that outcome. And just as a meteorologist updates their forecast after seeing a new weather map, you update your quantum beliefs using a simple logical rule called Bayes' theorem. Every time you get new data from an experiment, you refine your expectations. The so-called collapse of the wave function is nothing mysterious. It is simply the moment when you learn something new and adjust your mental picture accordingly. The electron was always in a definite state. You just did not know which one. The moment of measurement removes your uncertainty. In QBism, the observer is not a special consciousness that forces reality to choose. The observer is just an agent, a participant, who is using quantum mechanics to navigate their own experience. This might sound similar to the Copenhagen interpretation, but there is a crucial difference. Copenhagen treats the wave function as a description of a quantum system, even if it is only about what we can measure. QBism goes further and says the wave function is about the user, not the world. It is a statement of your expectations, not a picture of objective reality. This shift completely dissolves the measurement problem. There is no need to explain how a real wave function collapses because there is no real wave function to collapse. The only question is how you, as an agent, should update your beliefs when you encounter new evidence. Critics argue that this makes quantum mechanics too subjective, that it risks turning science into a collection of personal opinions. But supporters point out that the rules for updating beliefs, the Bayesian logic, are universal and mathematically rigorous. Two agents with the same data will arrive at the same probabilities, so the theory still gives consistent, objective predictions. The real world remains shared and public. QBism just says that the quantum state is a bridge between the private experience of the agent and the public outcomes of experiments. In this view, the universe is not a machine waiting to be discovered. It is a participatory drama, and each of us is a player armed with a quantum recipe for making sense of what we see. This leads to a profound and unsettling thought. If the wave function is only about your expectations, then what is the world really like independent of any agent? QBism does not answer that. It simply says that question might be beyond the reach of physics. And that quiet admission opens the door to an even more radical possibility, one that questions the very fabric of space and time. That last idea, that the quantum state is a tool for a participant rather than a feature of the world, already pushes us toward a more relational view of reality. But the Italian physicist Carlo Rovelli took this logic one step further and built an entire interpretation around it. In his relational quantum mechanics, there is no such thing as an absolute quantum state. A state exists only relative to a particular observer, where observer can mean any physical system, from a human scientist down to a single atom. The same system can be in a superposition from one perspective and in a definite state from another, and both descriptions are equally valid. There is no need for a universal wave function that captures everything at once. Every interaction between two systems defines a kind of local reality, a shared fact that holds only for those two systems at that moment. For a third system looking in from outside, the situation may look completely different. This dissolves the measurement problem in a clean and elegant way. When you measure an electron, you and the electron become entangled. From your perspective, the electron now has a definite spin. But from the perspective of a distant observer who has not interacted with either of you, the whole system of you plus the electron remains in a superposition. There is no contradiction. Each perspective is correct within its own relational context. The only time you need to worry is when the distant observer later interacts with you, and then that interaction will define a new set of relational facts that reconcile the two views. This approach naturally fits with Einstein's theory of relativity, where simultaneity and time are also relative to an observer's motion. Rovelli has often pointed out that just as special relativity showed that time is not absolute but depends on your frame of reference, relational quantum mechanics shows that the quantum state is not absolute but depends on your relational frame. Both theories ask us to let go of a single, God's eye view of the universe. What remains is a network of relations, a web of interactions where every property is a kind of mutual agreement between systems. There is no ultimate ground. Reality is nothing more than the sum of all these relative facts. That is a deeply democratic picture of the cosmos. No system has a privileged perspective. Not even a conscious observer, an atom interacting with a photon creates a relational fact just as valid as any human measurement. It is a world built from relationships, not from pre-existing substances. And this relational view opens the door to an even more radical possibility, one that asks whether space and time themselves might also be relative, not just to observers but to the very fabric of knowledge itself. Consistent histories takes a different approach, keeping a single objective reality at the center. This interpretation says that the universe is a single, unfolding story made up of many possible sequences of events, which physicists call histories. A history is simply a sequence of states that a quantum system passes through over time, like the positions of a particle at different moments, but not every possible history is physically meaningful. Only those that satisfy a very strict condition called consistency are allowed to contribute to reality. If two histories are inconsistent, they interfere with each other in a way that makes it impossible to assign them both a real probability. Think of it like a detective trying to reconstruct a crime from conflicting witness statements. Some accounts contradict each other so strongly that they cannot both be true. The detective discards them and only keeps the narratives that fit together into a single coherent timeline. In consistent histories, the quantum world works the same way. The equations of quantum mechanics generate a vast number of potential histories, but the consistency condition filters out all but a set of mutually compatible ones. These surviving histories then form a consistent family, and within that family, each history has a well-defined probability. This approach completely eliminates the need for wavefunction collapse. Measurement is not a special event where reality suddenly snaps into focus. It is simply a process of coarse graining, looking at the system at a larger scale where many fine details of the history become irrelevant. Just as a map of a city does not show every single crack in the pavement, a measurement in quantum mechanics picks out only the broad features of a history that are relevant to the observer. The fine-grained details remain, but they are averaged over or ignored. The strength of this interpretation becomes most apparent when dealing with closed systems, meaning systems that have no external environment or observer. The entire universe itself is the ultimate closed system. There is no outside observer to cause a collapse, so how do we describe the quantum state of the cosmos? Consistent histories gives a natural answer. The universe has a set of consistent histories, each describing a possible evolution from the Big Bang to the present and beyond. The probabilities of these histories are built into the equations from the start, and no collapse ever occurs. This makes the interpretation very attractive for quantum cosmology, the study of the universe as a whole. It allows physicists to ask questions about the early universe without worrying about who was there to measure it. Yet despite its success in handling the universe, consistent histories still leaves many physicists uneasy. It requires a precise mathematical definition of consistency, and that definition can be surprisingly tricky to apply in realistic scenarios. More importantly, the interpretation insists that there is a single objective reality, a unique set of histories that actually happened. But if many families of consistent histories are possible and they cannot be combined, how do we know which one corresponds to the real world? The interpretation does not give a clear answer. It simply says that any consistent family is a valid description and that we choose the one most useful for the question we are asking. This pragmatic flexibility is both a strength and a weakness. It lets us model the universe without philosophical baggage, but it also raises the same question that has haunted every interpretation from the very beginning. Is the universe telling one story or many? And if many, why do we only experience one? But what if the arrow of time itself is not a one-way street? What if quantum events involve a handshake that reaches both forward and backward through time? This is the startling proposal at the heart of the transactional interpretation, developed by physicist John Cramer in the 1980s. Kramer took inspiration from a much older idea in electromagnetism, one that had been around since the early 20th century. In standard physics, when an electric charge accelerates, it sends out ripples called retarded waves, which travel forward in time and carry energy away from the source. But the equations of electromagnetism also allow an equal and opposite solution, advanced waves, which travel backward in time. Physicists usually discard these advanced solutions as unphysical because they seem to violate causality. Kramer argued that in the quantum realm, both types of waves are real and necessary. When an emitter, say an electron about to make a transition, prepares to release a quantum of energy, it sends out a retarded wave that moves forward in time. This is called the offer wave. It travels outward through spacetime, spreading like a ripple in a pond until it encounters a potential absorber, another particle that can accept the energy. The absorber then responds by sending back an advanced wave, a confirmation wave that travels backward in time along the exact same path. This confirmation wave arrives at the emitter at the exact moment the offer wave was launched. The two waves form a kind of quantum handshake, a closed loop that locks in the transaction. The result is a real transfer of energy, momentum, and information from the emitter to the absorber. The transaction is complete. The wave function is no longer a ghostly probability. It is a real field that spans spacetime, and the handshake is the mechanism that turns potential into actuality. This picture elegantly explains non-locality without needing faster-than-light signals. When two particles are entangled, a measurement on one particle creates an offer wave that reaches out across space, finds the other particle as an absorber, and receives a confirmation wave that travels backward in time to seal the transaction. The correlation is instantaneous because the handshake occurs across the entire interval between the two events, and the confirmation wave, moving backward in time, effectively collapses the wave function at both ends simultaneously. There is no need for spooky action. It is a purely causal, time-symmetric process. The transactional interpretation also offers a fresh perspective on the arrow of time. In everyday life, we remember the past and not the future. We see entropy increase, we feel time flow forward. But in Kramer's picture, the arrow of time emerges from the direction of the handshake. The offer wave moves forward, the confirmation wave moves backward, and the transaction itself is timeless, a complete unit that includes both ends. Our perception of forward time may simply be a consequence of the fact that we are made of particles that act as absorbers, always receiving confirmations from the future. This interpretation appeals to many physicists because it restores a sense of causality, albeit one that weaves through time in a way our intuition finds strange. It treats advanced and retarded waves symmetrically, giving both equal physical status, and it provides a concrete mechanism for wave function collapse, turning it into a real physical event, a handshake that bridges the gap between potential and reality. Yet it has its critics who point out that the theory demands a universe filled with absorbers for every quantum event. If an offer wave never finds an absorber, does the transaction fail? In an expanding universe, some light from distant stars may never reach an absorber. Kramer's model requires that all offered waves eventually find a home, or else the picture breaks down. This is an open question, one that connects quantum mechanics to cosmology in surprising ways. But for now, the transactional interpretation stands as one of the most imaginative and time-bending ideas in the quantum toolbox, a vision where past and future reach toward each other and shake hands. Nature itself seems to prefer certain quantum states, and that preference may be the key to how we experience a classical world. This is the core insight of quantum Darwinism, an idea developed by physicist Wojciech Zurek over the past few decades. Zurek asked a question that seems simple but cuts to the heart of the measurement problem. If the quantum world is full of superpositions and fuzzy possibilities, why does our everyday world look so definite, so classical, so solid? His answer is that the environment itself acts as a kind of selective filter, a ruthless editor that favors some quantum states over others. To understand this, we have to look at what happens when a quantum system interacts with its surroundings. That interaction is called decoherence. In standard quantum mechanics, a particle in superposition will quickly become entangled with the countless particles in its environment, with air molecules, with photons, with the walls of the room. This entanglement is not a bug. It is a feature that explains why we never see a cat that is both alive and dead. The environment essentially records the state of the system, making a vast number of copies of certain pieces of information. But not all quantum states are equally good at surviving this process. Some states are incredibly fragile. A tiny nudge from a passing photon, and their superposition collapses into a mess. Other states are robust. They resist entanglement and remain stable even after repeated interactions with the environment. Zurek calls these pointer states. They are the states that get selected, the ones that can persist and proliferate. Think of it like a species in an ecosystem. Some genetic traits are fragile and quickly die out. Others are resilient and spread through the population. The environment, in a sense, performs natural selection on quantum states. The pointer states are the fittest, the ones that can replicate themselves by imprinting copies of their information onto the surrounding environment. Every time a photon scatters off a particle in a pointer state, that photon carries away a tiny piece of information about that state. Over time, the environment becomes saturated with copies. The information becomes redundant. You can look at a single photon or 1,000 photons, and each one will tell you the same thing. The particle is in this position with this momentum. That redundancy is what makes the state objective. Any observer anywhere can measure a sample of the environment and get the same result. The state is no longer tied to one observer's perspective. It is a public fact, a piece of shared reality. This is the moment when the quantum becomes classical. The measurement process, which once seemed like a mysterious act of consciousness causing collapse, is reframed as something much more mundane. A measurement is simply an observer acquiring information that is already present in the environment, information that was copied and proliferated by the interaction between system and surroundings. There is no collapse at all. The wave function of the system never snapped into a single state. It just became entangled with so many environmental degrees of freedom that the superposition spread out and became inaccessible to any practical observation. The pointer state, the one with the redundant copies, is the only one we can extract. This is a deeply satisfying picture. It explains why our world looks classical without invoking any special role for observers. The universe does not need a conscious mind to pin down reality. It just needs an environment that is big and messy enough to act as a giant copying machine. And that is exactly what we have. Every object around you is constantly bombarded by light and air and radiation. Each interaction leaves a trace, a fingerprint that encodes the object state. Those fingerprints spread, multiply, and become the objective facts that we all agree on. The classical world is not a separate realm. It is the quantum world seen through the lens of decoherence and environmental selection. Zurek himself has called this a shift from thinking about states to thinking about information. Reality, in this view, is built from the patterns of information that survive the relentless copying process. And that shifts the question from why does the wave function collapse to why do some pieces of information become objective? The answer leads us back to the environment, the great selector, which quietly decides what is real and what remains a ghostly potentiality. Decoherence is the engine behind environmental selection, but it is not a full theory on its own. To understand why, we have to look at what decoherence actually does. It is a physical process that happens whenever a quantum system interacts with its surroundings, which is basically all the time. Take a particle in a superposition of two positions. As soon as that particle touches even a single air molecule, the two possibilities start to get entangled with the molecule. The molecule flies off in one direction if the particle is here, and in a slightly different direction if the particle is there. That molecule then bumps into another molecule and another, and within a fraction of a nanosecond, the information about the particle's position has spread across billions of particles. What was a clean superposition becomes a messy, tangled web of correlations. This is decoherence. It rapidly suppresses the quantum coherence that makes superpositions behave strangely. Before decoherence, the two parts of the wave function could interfere with each other, producing the famous wave-like patterns. After decoherence, that interference is gone. The two possibilities no longer overlap. They become separate, non-interacting branches, and from the perspective of any observer who only has access to a small part of the environment, the system looks exactly like a classical mixture, a statistical blend of two definite states. You might think that solves the measurement problem. After all, we never see superpositions in daily life because decoherence destroys them almost instantly. But here is the catch: decoherence does not pick one outcome. It does not tell the universe which branch is real. It only spreads the superposition so wide that we cannot see both branches at once. The wave function still contains both possibilities, just entangled with a vast number of environmental particles. To go from a mixture to a single actual result, you still need something else: a collapse, an observer, a handshake, or a splitting of worlds. Decoherence is like a master stagehand who arranges the scenery and dims the light so that only one scene is visible to the audience, but the other scenes are still back there waiting. That is why decoherence is not an interpretation of quantum mechanics on its own. It is a mechanism, a crucial ingredient that every serious interpretation must incorporate. Many worlds uses decoherence to explain why the branches do not interfere. Consistent histories uses it to define when a history is consistent. Objective collapse theories use it to determine the threshold for spontaneous localization. Even Copenhagen, in its modern form, acknowledges decoherence as the reason measurement apparatuses appear classical. Decoherence gives us a powerful tool for understanding why the quantum world looks classical at human scales, but it leaves the deepest mystery untouched. The universe still has to choose or not choose which path is real, and that is where the interpretations truly part ways, each one building upon the platform that decoherence provides. One bold variant proposes that only the mind splits, not the physical world. This is the many minds interpretation, a cousin of Everett's multiverse that tries to solve a deep puzzle. In standard many worlds, the entire universe branches at every quantum event, creating countless physical copies of everything, including every observer. But many minds asks a different question. What if the physical universe stays unified and only the conscious experience of each observer divides? Under this view, there is only one wave function for the whole cosmos. No physical branching occurs. Instead, each observer's mind is not a single entity but a continuous sequence of mental states, each corresponding to one possible outcome. When a quantum measurement takes place, the observer's consciousness follows one of the possible paths, while the other possibilities remain as unrealized potentials, never actualized in any mind. The physical apparatus, the particle, the environment all stay in a single superposition, but the observer only ever experiences one branch because that is the branch their mental state has selected. This elegantly sidesteps the need for physical splitting while still explaining why we see a definite result. The universe itself never chooses. It remains a fuzzy, overlapping haze. But each conscious being follows their own thread through that haze, and for them, that thread is the only reality they ever encounter. This interpretation has profound implications for the nature of consciousness and identity. If your mind splits at each moment, then you are not a single, continuous self. You are a bundle of mental trajectories, each branching quietly. The you reading this sentence is just one such trajectory, and all the other versions of you, the ones who stopped reading, the ones who never watched this video, are equally real but forever inaccessible to your experience. This raises the question of what makes a person the same person over time. If a new branch appears every instant, is there any continuity at all? Many mind supporters argue that the experience of continuity is an illusion created by the overlap between successive mental states. Each moment's mind shares enough memories and dispositions with the previous moment to feel like a single life, but the underlying structure is a dense bush of branching experiences. The interpretation also attempts to solve the probability problem that haunts many worlds. In Everett's original picture, if every outcome happens in some branch, it is not obvious why we should assign probabilities to outcomes at all. Why does a 90% chance feel any different from a 10% chance if both happen for sure in some universe? Many minds answers by appealing to subjective experience. The physical wave function does not have probabilities, but the mental experience of an observer does. The observer's mind will follow each branch with a frequency that matches the Born rule, the standard quantum probability law, because that is how consciousness weighs the possibilities. You feel that a 90% outcome is more likely because across the ensemble of your future mental states, 90% of them will experience that result. The probability is not out there in the world, it is a property of your own limited perspective. This makes the interpretation deeply personal. It centers consciousness as the filter through which quantum uncertainty becomes lived certainty. And it raises a question that has no easy answer. If the physical universe does not split, then where do the other mental branches go? They are not stored anywhere in the cosmos. They are simply not experienced. The universe remains a single, silent wave, and only the minds that ride it give it color and meaning. That is a strange and beautiful picture, one where reality itself is impersonal and indifferent, and all the stories we tell ourselves are just the paths our minds happen to trace. From that deeply personal vision of branching minds, it is only a small step to one of the most unsettling ideas ever to emerge from quantum theory. If the many worlds interpretation is correct and every possible outcome of a quantum event plays out in a separate branch, then what happens to an observer who faces a life-threatening situation? The logical answer, at least within the framework of many worlds, is that the observer never experiences their own death. This is the core of the quantum immortality thought experiment, a chilling extension of Everett's multiverse that has haunted philosophers and captured the imagination of science fiction writers for decades. The reasoning goes like this. Imagine a person sits down in a chair with a gun pointed at their head. The gun is rigged to a quantum random number generator, say a device that measures the spin of an electron. If the electron is spinning up, the gun fires and the person dies. If the electron is spinning down, the gun clicks harmlessly and the person lives. In standard quantum mechanics, there is a 50% chance of each outcome. But in many worlds, both outcomes are real. In one branch, the person dies. In another branch, they survive. Now here is the crucial twist. The person who dies can never experience that outcome because there is no conscious observer left in that branch to have an experience. From the first-person perspective of the person in the chair, they will only ever perceive the branch where they survive. Even if the odds of survival are astronomically low, as long as there is a non-zero probability, there will be a branch where they continue to exist. Extend this logic to a chain of such tests. Suppose 100 trials are performed, each with a 50% chance of death. In classical probability, the chance of surviving all 100 rounds is basically 0, 1 in 2 to the 100th power. But in many worlds, there is still a branch where the person wins every single toss. And from that person's subjective perspective, they experience that winning streak as a miraculous run of luck. They never encounter the branches where they died because those branches contain no conscious witness. The conclusion is that any conscious observer following the logic of many worlds should expect to continue surviving indefinitely. No matter how deadly the situation, there will always be at least one branch, however improbable, where the observer escapes. This is quantum immortality, the idea that your consciousness is effectively immortal, forever veering away from death along the narrow paths of possibility. The thought experiment is often paired with the concept of quantum suicide, which is the idea of using such a device to test the many worlds interpretation. If many worlds is true, a person who sits in the chair should never observe the outcome where they die, so they will see the gun fail every time. But a person watching from the outside would see the gun sometimes fire and the person die. There is no contradiction because the observer and the subject are in different branches. However, the experimental subject would never be able to report the result because the only branches where they survive are ones where the observer also sees them alive. The test is logically impossible to complete, which is why quantum suicide remains a thought experiment, not a real experimental protocol. This idea has gained a cult following in both science fiction and philosophical discussions about the nature of death and identity. Novels and films have explored the premise of a person who cannot die, who survives plane crashes and fatal diseases through sheer quantum luck, but the concept rests on a series of controversial assumptions. First, it assumes that all branches of the wave function are equally real, and that consciousness follows one specific branch without any mechanism to jump between them. Second, it assumes that personal identity is tied solely to the continuity of subjective experience, ignoring the fact that physical continuity of the body is broken across branches. Third, it ignores the possibility that quantum events that lead to survival may become so rare that the required brain states would be unrecognizable as a human mind, perhaps degenerating into a barely conscious fragment. Most physicists treat quantum immortality as a fascinating philosophical puzzle rather than a genuine prediction of many worlds, but the thought experiment forces us to confront an uncomfortable question. If the universe truly branches at every quantum event, then what does it mean to say that someone has died? From the outside, death is a statistical certainty. From the inside, it may never happen. And that strange asymmetry between the view of the universe and the view of the self is one of the deepest and most haunting legacies of the many worlds interpretation. Einstein found the many worlds idea deeply troubling, but he had his own quantum rebellion. In 1935, along with his colleagues Boris Podolsky and Nathan Rosen, he published a paper that seemed to expose a fatal flaw in the standard view of quantum mechanics. Their argument, now famous as the EPR paradox, began with a simple question. If quantum mechanics is complete, meaning it describes everything there is to know about a system, then how can two particles that have interacted become linked in such a way that measuring one instantly determines the state of the other, even if they are separated by light years? Einstein and his co-authors reasoned that this spooky action at a distance could not be real. Instead, they argued, the particles must carry hidden properties, secret instructions written into them at the moment they interacted that predetermine what any measurement will find. These hidden variables would make quantum mechanics an incomplete theory, just a statistical description of deeper, deterministic facts. To Einstein, this was the only sensible conclusion. The moon exists whether you look at it or not, and so should the spin of an electron, but the EPR argument had a hidden assumption. It assumed that the hidden variables could not influence each other across great distances faster than light. This is called locality, the idea that objects are only affected by their immediate surroundings. For decades, physicists debated whether local hidden variables could actually reproduce all the predictions of quantum mechanics. The question remained purely theoretical until 1964, when a young physicist named John Bell devised a brilliant test. Bell showed mathematically that if local hidden variables were real, then the correlations between measurements on entangled particles would obey a specific inequality. If the inequality was violated, then local hidden variables were impossible. The only loophole was that the hidden variables would have to be non-local, acting instantly across any distance. Experimentalists soon put Bell's inequality to the test. Starting in the 1970s and continuing to this day, experiments with photons and atoms have consistently shown that the inequality is violated. The correlations are stronger than any local hidden variable theory can explain. This means that if hidden variables exist, they must be non-local, just like the pilot wave in David Bohm's theory we discussed earlier. The universe is fundamentally connected. A measurement here can instantly affect a particle over there, not because a signal travels, but because the two particles are part of a single quantum system woven together across space. The EPR paradox did not disprove quantum mechanics. It clarified something far deeper. Reality, at its most fundamental level, is non-local, and that non-locality is not a bug to be fixed. It is a feature that every interpretation must confront. Some interpretations embrace non-locality openly, like Bohmian mechanics. Others try to explain it away through branching worlds or relational perspectives. But the EPR argument, and Bell's resolution of it, stands as one of the most important crossroads in the history of physics. It forced us to let go of the comfortable idea that the universe is a collection of isolated particles minding their own business. Instead, we now see hints of a web of influence that binds everything together quietly, instantly, and forever. And that revelation opens the door to even stranger possibilities, including the idea that the entire universe might be a single, entangled whole. Superdeterminism takes this entanglement to its most radical conclusion, where Bell's theorem proved that any local hidden variable theory must violate a certain inequality. Quantum experiments show that inequality is indeed violated. But Bell's proof relied on a crucial assumption. The measurement settings themselves, the choices of which direction to measure a particle's spin, are independent of the hidden variables that determine the outcome. In standard quantum experiments, those settings are chosen randomly, often by a quantum random number generator or even by the light from distant stars. The assumption is that this randomness is disconnected from whatever hidden properties the particles carry. Superdeterminism says that assumption might be wrong. What if the hidden variables are correlated with the measurement settings from the very beginning? What if the entire universe, from its initial conditions, has been set up so that every measurement setting and every particle property are linked in a single, inescapable pattern? In that case, Bell's inequality would not apply because the statistical independence required for the proof would be violated. The universe could be perfectly local, with no faster-than-light signals, yet still produce the strange correlations we observe in experiments. The price for this elegant escape is enormous. It means that the cosmos is a single, fully correlated system where every event, every decision, every seemingly random choice is already tied to every other event. Our belief that we freely choose which measurement to perform becomes an illusion. The experimenter who decides to measure spin up instead of spin down, the random number generator that selects an angle, even the decay of a radioactive atom used to trigger the choice, all of these are pre-correlated with the hidden states of the particles they are about to measure. The universe looks like a vast conspiracy where everything is secretly coordinated to make quantum mechanics appear non-local when it is actually just deeply, globally predetermined. Most physicists find this idea deeply unsatisfying. It feels like cheating, invoking a kind of cosmic collusion that cannot be tested, and that undermines the very foundation of scientific experimentation. If we cannot trust that our measurement settings are independent of what we are measuring, then no experiment can ever be trusted. We would be trapped in a hall of mirrors where every result merely reflects a preordained script. Yet superdeterminism remains logically consistent. It cannot be ruled out by any experiment because any experiment would itself be part of the correlation. It is a bulletproof philosophical position, but one that seems to sacrifice the very notion of free experimenter choice. For that reason, it is usually pushed to the fringes of physics, a last resort for those who find non-locality too distasteful. But its very existence reveals something important. The foundation of quantum mechanics rests on assumptions that are not proven, only assumed. And as long as those assumptions remain unproven, the door stays open, even if just a crack, for a universe that is not only entangled but also, in a quiet and hidden way, predetermined. A different path avoids both hidden conspiracies and countless worlds. It is called the modal interpretation, and it tries to carve out a middle ground where reality is both definite and observer-dependent without multiplying universes or invoking invisible forces. At its heart, the modal interpretation makes a sharp distinction between two kinds of states. The first is the quantum state, the familiar wave function that evolves according to the Schrödinger equation and describes a landscape of possibilities. The second is the value state, a separate layer that tells you which properties are actually true of a system at any moment. The quantum state spreads out like a fan of potential futures. The value state picks one fan and says this property is real right now. To do this picking, the modal interpretation needs a preferred basis, a set of physical quantities that are always treated as having definite values. Common candidates are position or the energy levels of a system. This preferred basis is not chosen arbitrarily. It is often tied to the structure of the environment or to the macroscopic nature of the measuring device, ideas borrowed from decoherence theory. Once the basis is fixed, the value state evolves according to a stochastic process. That means it jumps randomly from one set of definite values to another, and the probabilities of those jumps are given by the standard Born rule. So the modal interpretation offers a realist picture. Objects have properties whether or not anyone measures them, yet it does not add hidden variables because there is no additional mechanism smuggling in extra information. The value state simply selects which branch of the quantum state counts as actual. It also does not require a multiverse. Only one set of properties is real at a time, the one picked out by the value state. The other branches in the quantum state remain as mere possibilities, not as actual parallel worlds. This makes the modal interpretation philosophically tidy. It explains why we see a classical world without invoking collapse, consciousness, or branching. But it comes with its own challenges. The stochastic jumps are essentially random, so the theory does not tell you why a particular property becomes actual, only that it does with some probability. And the need for a preferred basis feels somewhat artificial. Why should position be special and not momentum? Different choices lead to different physical predictions, so the interpretation must be supplemented with a physical rule for picking the right basis. Proponents often turn to quantum logic, a framework that reworks the logical rules we use to reason about quantum systems. In ordinary logic, a statement is either true or false. In quantum logic, the structure of propositions is non-distributive, meaning you cannot always combine them the way you would in everyday reasoning. The modal interpretation aligns with this view by treating the value state as a kind of logical assignment, a way of saying which propositions about a system are actually true, given the constraints of the quantum state. For those drawn to a realist but conservative picture, the modal interpretation offers a quiet alternative. It does not shout about parallelism or hidden mechanisms. It simply says that the quantum world contains both potential and actual, and that the actual is a kind of random but law-governed selection from the potential. It is a subtle, almost understated vision of reality, one that asks us to accept a fundamental randomness in what becomes real, while still letting us hold onto the idea that things are, in fact, real. Quantum logic makes a radical claim about the very rules of reasoning itself. It argues that the logic we use to think about quantum systems should be different from the logic we use in everyday life. In classical logic, every statement is either true or false. A cat is either alive or dead. A particle is either here or there. This is the law of the excluded middle, and it works perfectly for tables and chairs. But quantum experiments show that an electron can be in two places at once. A particle can be spinning both up and down simultaneously. If you try to force that into classical logic, you end up with contradictions. You have to say that a statement like the electron is here, and the statement the electron is there are both true and false at the same time, which is nonsense in ordinary reasoning. Quantum logic avoids this by changing the underlying structure of how propositions connect. In Hilbert space, the mathematical space where quantum states live, the set of all possible propositions about a system forms a lattice of subspaces. This lattice is not a Boolean algebra, which is the structure of classical logic. In a Boolean algebra, a proposition and its negation always cover all possibilities. But in the quantum lattice, the negation of a proposition is not simply the complement. Instead, the relationship between propositions is much more subtle. For example, the proposition that a particle has a certain position and the proposition that it has a certain momentum cannot both be sharply defined at the same time. In classical logic, you could combine them with and. In quantum logic, that combination is not a valid proposition because the two properties do not have a common eigenstate. The measurement problem from this perspective arises because we try to apply classical logic to a quantum world. When we measure a particle, we force it into a classical state, and we describe that state with classical propositions. But the particle itself, before measurement, obeys a different logical structure. The so-called collapse of the wave function is not a physical event. It is a translation error. We are translating a quantum logical proposition into a classical one, and the translation rule is the Born rule. This interpretation does not add any new physical mechanisms. It does not postulate hidden variables or multiple worlds. It is a formal framework, a rewrite of the language we use to describe experiments. It was developed by the mathematician Garrett Birkhoff and the physicist John von Neumann in the 1930s, and it has influenced deep philosophical work on the nature of reality and truth. Critics argue that quantum logic does not actually solve the measurement problem because the translation rule itself still needs a physical justification. But it has inspired a rich tradition of thinking about whether the world itself is fundamentally non-classical in its logical structure. It challenges the idea that our everyday logic is universal. And that challenge opens a question that echoes far beyond physics. If the laws of reasoning can change depending on the domain, then what else about our understanding might be contingent on the scale we happen to inhabit? The quantum logic interpretation reshapes the rules of reasoning, but string theory reshapes the very fabric of possibility itself. This is not a direct answer to the measurement problem, but rather a sweeping vision of what reality might contain on the largest scales, a landscape of universes born from the geometry of invisible dimensions. String theory began as an attempt to unify quantum mechanics with general relativity, to describe the fundamental particles as tiny vibrating strings. The mathematics required something extraordinary to work. The equations demanded extra dimensions beyond the familiar 3 of space and 1 of time. When theorists explored how those extra dimensions could be curled up or compactified, they discovered that the shape of this curling determined the properties of the universe that emerges. The size of the extra dimensions, their curvature, the way they twist and fold, all of these choices directly set the values of fundamental constants like the strength of gravity, the mass of the electron, the force that binds atomic nuclei together. And here is the shocking part. There is not just one way to compactify those dimensions. There are an astronomical number of possibilities, roughly 10 to the 500th power or more. Each distinct configuration is called a vacuum, and each vacuum corresponds to a complete universe with its own set of physical laws. This collection is known as the string theory landscape. It is a multiverse not of branching histories but of separate, disconnected realities, each with different constants, different particles, different chemistry, and perhaps different laws of physics entirely. Our universe is just one tiny island in this vast ocean of possibilities. Why then do we find ourselves in a universe so finely tuned for life? The constants of nature seem precisely balanced. If gravity were slightly stronger, stars would burn too fast and collapse. If the expansion rate of the early universe were a tiny fraction different, galaxies would never form. This fine-tuning has puzzled physicists and philosophers for decades. The landscape offers an elegant but controversial explanation. With so many universes, each with random constants, it is inevitable that a tiny fraction will have the right conditions for life. We naturally find ourselves in one of those rare habitable pockets, not because the universe was designed for us, but because we could not exist anywhere else. This is the anthropic principle applied to a cosmic scale. It is a powerful idea, but it also raises a deep challenge. If the landscape is real, then we can never directly observe the other universes. They are cut off from us by the very geometry of the extra dimensions. String theory then becomes a theory that predicts a multiverse we cannot test. Some physicists find this deeply unsatisfying. Others embrace it as a natural consequence of the mathematics. Regardless, the string theory landscape dramatically expands what we mean by reality. The universe is not just the space we see. It is a vast, hidden structure of dimensions and vacua where every possibility that can exist does exist somewhere beyond our reach. This shift in scale from particles to dimensions to landscapes prepares us for an even stranger idea, one where our entire cosmos might be just a simulation running on a machine more advanced than we can imagine. The universe we call home may be nothing more than a membrane, a thin slice of reality floating in a higher dimensional sea. This idea, known as brane cosmology or the ekpyrotic universe, turns the Big Bang into something far more ordinary, a collision between two such membranes. In this picture, our familiar three dimensions of space are just one brane, a kind of sheet, embedded in a larger space called the bulk, which contains at least one extra dimension. Another brane floats nearby, maybe just a hair's breadth away in that hidden dimension. Every so often, these two branes drift toward each other and smash together. The impact releases an enormous burst of energy, heating the branes to extreme temperatures and creating the fireball we call the Big Bang. After the collision, the branes rebound and the expansion of our universe begins. The cycle can repeat endlessly, with branes colliding, separating, and colliding again, each time producing a new universe with its own beginning. This scenario offers a radical alternative to the standard inflationary model of the early universe. Instead of a single, unique moment of creation, we get a rhythmic, cyclic cosmos where time stretches back infinitely. The key insight comes from string theory, which predicts that our universe could be a brane, a three-dimensional island in a higher dimensional ocean. The collision itself is not a random accident. It is governed by a quantum potential, the same kind of wave function that describes particles in quantum mechanics. In fact, proponents of the ekpyrotic model argue that the entire multiverse of branes can be described by a single quantum state, a wave function of the cosmos that evolves according to its own Schrödinger equation. This wave function does not collapse, it simply spreads and interferes, and our universe is one particular branch, one history, emerging from that entanglement of branes. What makes this theory especially compelling is that it makes testable predictions. The collision between branes would leave a specific signature in the cosmic microwave background radiation, the faint afterglow of the Big Bang. Those signatures include a particular pattern of temperature fluctuations, a non-Gaussian distribution of hot and cold spots, subtly different from what inflationary theory predicts. Future space missions like the European Space Agency's Planck satellite have already searched for these patterns. So far, the data is consistent with both inflation and the ekpyrotic model, but as precision improves, we may be able to distinguish between them. If the ekpyrotic universe is correct, then the hidden dimensions of string theory are not just a mathematical curiosity. They are the stage on which the drama of creation unfolds. Our universe is not alone. It is one among many, born from collisions, separated by thin gaps in extra dimensions that we cannot directly see but whose effects ripple through the fabric of space and time. This vision ties together quantum mechanics, gravity, and cosmology into a single, breathtaking picture, one where the beginning of everything is not a singular event but a recurring process, a cosmic heartbeat. And that heartbeat raises a new question. If brains can collide and produce universes, can they also slide past one another without touching, creating ghostly interactions that echo across dimensions? That possibility leads us to the idea of parallel brains, worlds so close yet so far that they might influence each other in ways we are only beginning to explore. Our entire universe might be a hologram. That is not a metaphor or a poetic flourish. It is a serious scientific proposal that emerged from the study of black holes, the most extreme objects in the cosmos. In the 1970s, the physicist Jacob Bekenstein made a startling discovery. When matter falls into a black hole, the black hole's surface area increases, and that increase seems to encode the information about everything that went inside. Later, Stephen Hawking showed that black holes radiate energy and slowly evaporate, raising the question of what happens to the information trapped within. The resolution came from an unexpected direction. Theorists realized that the maximum amount of information that can be stored in a region of space is not proportional to its volume, but to the area of its boundary. In other words, the three-dimensional interior of a black hole can be fully described by the two-dimensional surface that surrounds it. This is the holographic principle, and it suggests that our entire universe, with its three dimensions of space and one of time, might be a kind of projection from a two-dimensional surface at the cosmic horizon. The most concrete mathematical realization of this idea comes from a specific scenario called anti-de Sitter space, a negatively curved universe that mathematicians and physicists use as a theoretical playground. In 1997, Juan Maldacena proposed the AD/S/CFT correspondence, a precise equivalence between a universe with gravity in 5 dimensions and a quantum field theory without gravity on its 4-dimensional boundary. Every calculation in one framework has an exact counterpart in the other. A black hole crashing in the 5-dimensional space corresponds to a hot, swirling plasma on the boundary. A particle moving in the interior corresponds to a ripple in the quantum field. The two descriptions are dual, meaning they are the same reality seen from different angles. This correspondence has become one of the most powerful tools in theoretical physics, allowing researchers to solve problems in strongly interacting quantum systems by translating them into easier gravitational problems. But the implications go far beyond mathematical convenience. If our own universe is approximately anti-de Sitter, or if its cosmic horizon behaves similarly, then our three-dimensional reality might be a holographic projection of information encoded on a distant surface. Every particle, every star, every thought you have could be a manifestation of data written in a lower dimensional language. This idea radically reframes the nature of space. Space is not a fundamental stage on which events play out. It is an emergent property, a kind of illusion generated by the entanglement between quantum degrees of freedom on the boundary. Time, too, may be emergent, a dimension that arises from the ordering of those quantum states. The holographic principle offers a potential bridge between quantum mechanics and gravity. Gravity becomes a kind of emergent force, a consequence of the information structure of the universe, not a fundamental interaction. It also provides a natural way to understand the black hole information paradox. Information is never lost because it is always preserved on the boundary surface, even as the black hole evaporates. For those who work on quantum gravity, the holographic principle is not just a wild idea. It is a guiding philosophy, a compass pointing toward a deeper theory that might one day unify all of physics, and it forces us to ask an unsettling question. If everything we experience is a projection, then what is the projector? What is the fundamental reality that casts this cosmic hologram? The boundary itself is still a quantum system governed by its own laws. So the mystery does not disappear, it simply moves one level deeper. From that holographic foundation, a more direct question emerges. What if our universe is not just a projection but a program? This is the simulated universe hypothesis, an idea that philosopher Niels Bohr brought into mainstream conversation in 2003. Bohr argued that if any civilization ever reaches a stage of technology where it can run realistic simulations of conscious beings, then the number of simulated minds could easily dwarf the number of biological minds. If that is true, then the odds that we are living in the base reality, the original, unsimulated universe, are astronomically small. We are far more likely to be inhabitants of a simulation run by some advanced intelligence. It is a simple and unsettling piece of reasoning. The logic rests on three possibilities, one of which must be true. Either civilizations almost never reach the technological stage where they can run such simulations, or they reach that stage but choose not to run them, or they do run them, and in that case we are almost certainly living inside one. Bohr himself does not claim to know which option is correct. He only lays out the probabilities, but the third possibility has captured the public imagination because it ties directly into our deepest questions about quantum mechanics. How does the simulation hypothesis connect to the quantum world? The link may lie in the idea of finite computational resources. Every simulation, no matter how advanced, must operate within limits. It cannot simulate every detail of a system down to infinite precision. There must be shortcuts, approximations, and algorithms that reduce the computational load. Some physicists have proposed that quantum phenomena might be exactly those shortcuts. In this view, the wave function does not represent a physical reality at all. It is a mathematical tool used by the simulation to manage uncertainty and to compute outcomes efficiently. Superposition is not a real state of matter, but a way for the simulation to postpone a decision. When you measure a particle, the simulation does not need to calculate its exact position until you look. It simply keeps all possibilities open using a probabilistic algorithm until an observation forces a specific answer. That sounds a lot like wave function collapse. The limits of the simulation also explain why we see certain features in the quantum world. The uncertainty principle, for instance, could be a direct consequence of the simulation's finite resolution. If the universe is rendered on a grid, a kind of cosmic pixel, then trying to measure both position and momentum with perfect accuracy becomes impossible because the grid simply does not have that information at that scale. Entanglement, too, might be a clever compression technique. Two particles that appear to be instantly connected could be stored in the same memory register, a single piece of code that updates both locations simultaneously. There is no faster than light signal because there is no distance between them in the underlying computational architecture. The non-locality we observe is just a byproduct of how the simulation stores and processes data. This idea is elegant because it explains so many quantum puzzles in one stroke, but it also raises a storm of philosophical consequences. If we are living in a simulation, then free will becomes a strange concept. Our choices might be fully determined by the code running behind the scenes. The feeling of making a decision could be just a script playing out, a subroutine that runs whenever a choice point is reached. On the other hand, if the simulation is truly sophisticated, our consciousness might still be emergent from the computational process. and our decisions could be genuinely free within the bounds of the code. The problem is that we have no way to tell the difference from the inside. That leads to a more profound difficulty. If we are simulated, then all of our evidence is also simulated. Every experiment we run, every particle we measure, every equation we derive is part of the same program. There is no independent test we can perform to check whether we are in a simulation, because the simulation would generate the results of that test too. The very concept of proof breaks down. This is why the simulation hypothesis is both fascinating and frustrating. It is a logical possibility that cannot be ruled out, but it also cannot be confirmed. It sits in a strange category of ideas that are untestable by their very nature, and yet it forces us to confront something deeply humbling. Our sense of reality, of being grounded in a solid, external world, may be nothing more than an illusion generated by processing power we cannot comprehend. Every quantum mystery we have explored in this video, the collapse, the entanglement, the branching, could simply be artifacts of the program, glitches in the matrix that hint at the underlying code. The universe we thought we were studying may be a classroom, a laboratory, or an art project built by minds far beyond our own for purposes we can only guess. And that leaves us with a final, open question. If we are inside a simulation, what happens when the program ends? The universe may be written in the simplest language of all, a language of ones and zeros. That proposal is the heart of digital physics, a view that challenges the very foundations of how we think about reality. For decades, physicists and mathematicians have assumed that space and time are smooth and continuous. You can zoom in on any point and then zoom in again forever, finding ever finer details without limit. Standard quantum theory relies on this continuous mathematics, using equations expressed in terms of infinite decimal expansions and infinitesimal changes. But what if that smoothness is only an illusion? What if beneath every phenomenon, from the spin of an electron to the expansion of galaxies, there is an underlying digital fabric, a vast cosmic grid of discrete bits like the pixels on a computer screen? This idea was championed by the physicist John Wheeler, who coined the famous phrase "it from bit." Wheeler argued that every physical thing, every it, ultimately derives its existence from bits of information, from yes or no answers to elementary questions. For him, the universe was not a stage where particles and fields play out their roles. Instead, the stage itself is made of pure information, and particles, forces, space, and time are all emergent patterns that arise when that information arranges itself in certain ways. Picture a cellular automaton, a simple grid of cells where each cell can be either on or off, 1 or 0. With just a few basic rules, such a grid can produce astonishingly complex behavior, from swirling patterns that mimic weather systems to self-replicating structures that look almost alive. The most famous example is Conway's game of life, where simple rules generate gliders, oscillators, and even patterns that can compute mathematical functions. Digital physics proposes that the real universe might be exactly this kind of discrete system, but on a scale far beyond anything we can simulate. Every cubic Planck length of space, the smallest possible volume, could be a single cell in a cosmic cellular automaton. The rules that govern how each cell flips between 1 and 0 would then determine everything we observe: the trajectory of a planet, the decay of a radioactive atom, the firing of a neuron in your brain. Space and time would not be fundamental. They would be coarse-grained approximations, statistical averages that emerge when you look at huge numbers of cells at once. The smooth geometry of Einstein's general relativity would be like the smooth surface of a pond, which appears perfectly fluid from a distance but is actually made of countless tiny water molecules in constant motion. This is a radical break from the continuous mathematics that underpins both classical and quantum physics. In quantum mechanics, the wave function evolves according to the Schrödinger equation, which is a smooth, continuous differential equation. It assumes that changes happen in infinitesimal steps across an infinitely divisible space and time. If the universe is truly digital, that equation is only an approximation, a useful fiction that works well at large scales but breaks down at the Planck scale, the realm where gravity and quantum effects meet. Some physicists have taken this challenge seriously and have tried to construct a fully digital version of quantum mechanics. One of the most prominent figures in this effort is Gerard T. Hooft, a Nobel Prize-winning physicist. T. Hooft has proposed that quantum mechanics might be a statistical description of an underlying deterministic cellular automaton. In his view, the apparent randomness of quantum outcomes arises because we are ignorant of the exact state of the automaton at the smallest scales. If we could see the full digital state, we would see a clockwork universe, deterministic and predictable. But we can only access a small part of that information, so we see probabilities and superpositions. This is similar to how the classical laws of thermodynamics emerge from the chaotic motion of molecules. We cannot track each molecule, but we can predict pressure and temperature. In the same way, the Schrödinger equation might be a thermodynamic approximation of a deeper, bit-based reality. T. Hooft's work is still controversial, and many physicists argue that it has not yet fully reproduced all the features of quantum mechanics, particularly non-locality and entanglement. But the effort points toward a profound possibility. If the universe is indeed made of bits, then the ultimate theory of everything might be a simple set of rules, a program that, when run, produces exactly the cosmos we observe. The mystery then shifts. We no longer ask why the laws of physics are what they are. We ask who wrote the program, or if the program is eternal and self-contained, why does it produce conscious observers who can wonder about their own origin? Those are questions that push digital physics beyond mere mechanics and into the realm of philosophy. For now, the idea that reality is computational remains a bold hypothesis, one that cannot be proven by any current experiment. But it reshapes how we see the universe. Every star, every breath, every thought may be a ripple in a sea of pure information, a story told in the simplest language of all. And that language, once we learn to read it, might reveal the deepest secrets of existence. The journey to understand those secrets takes us next to a completely different kind of theory, one that turns the entire notion of cause and effect upside down. One physicist argues that the clash between quantum mechanics and gravity holds the key to consciousness itself. Roger Penrose, a Nobel Prize-winning mathematician and physicist, has spent decades building a radical vision of reality that begins with a fundamental incompatibility. According to Penrose, the two great pillars of modern physics, general relativity and quantum mechanics, cannot both be correct as they currently stand. General relativity describes a smooth, curved spacetime where every object follows a deterministic path. Quantum mechanics describes a world of superpositions, probabilities, and wave functions that spread like fog. When you try to combine them, you get contradictions, infinities, and breakdowns. Most physicists believe these contradictions will only become apparent at absurdly high energies, near the Big Bang or inside a black hole. Penrose disagrees. He thinks the tension between the two theories is present everywhere, all the time, and that it manifests as a real physical process that collapses quantum wave functions. In his model, called objective reduction, every superposition of a massive object generates a tiny disturbance in the curvature of spacetime. The more massive the object, the larger the disturbance. Eventually, the two superposed versions of spacetime themselves become so different that they can no longer coexist. The system then makes a choice, collapsing into one definite reality. This is not a random hit from a hidden field, as in other collapse theories. It is a gravitational process, a fundamental instability built into the geometry of the universe itself. Penrose argues that this gravitational collapse happens on a specific timescale, roughly the time it would take for the two superposed mass distributions to separate by a Planck length, the smallest meaningful unit of distance. For a tiny particle, that timescale is enormous, billions of years, so superpositions persist easily. For a large object like a human being, the timescale shrinks to a tiny fraction of a second. This explains why we never see macroscopic superpositions in everyday life. The gravitational instability collapses them almost instantly. So far, this is a purely physical theory, independent of any observer or conscious mind. The wave function collapses because gravity demands it, not because someone looks. But Penrose then takes a dramatic step further, connecting this collapse process to the nature of consciousness. He proposes that the microtubules, tiny protein structures inside the neurons of our brains, are capable of sustaining delicate quantum states called superpositions for brief periods. When those superpositions reach the threshold set by Penrose's gravitational timescale, they collapse, and that collapse, he argues, produces a moment of conscious awareness. Each collapse corresponds to a distinct thought or experience. This idea is known as orchestrated objective reduction, or ORCH, a term that Penrose developed with the anesthesiologist Stuart Hameroff. In their view, the brain is not just a classical computer made of neurons firing. It is a quantum computer where microtubules process information in a deeply quantum way, and the collapse events are the fundamental units of consciousness. This is an extraordinary claim, and it has met with fierce skepticism, especially from neuroscientists. The overwhelming consensus in the neuroscience community is that microtubules are far too warm, wet, and noisy to sustain quantum coherence for any meaningful length of time. Quantum effects typically require extreme isolation and near absolute zero temperatures to persist. A living brain is a hot, chaotic environment, buzzing with thermal vibrations and chemical reactions. Most researchers believe that any quantum superposition in a microtubule would decohere in a femtosecond, a quadrillionth of a second, far too fast to play a role in thought or perception. Penrose and Hameroff have countered with arguments about quantum error correction and the possibility of a special type of coherence that resists decoherence, but the evidence remains thin. The theory has never been experimentally verified, and the few proposed tests have not produced clear results. Yet, despite the controversy surrounding the consciousness part, Penrose's gravitational collapse model itself is a serious, mathematically grounded alternative to the standard interpretations of quantum mechanics. It does not rely on an observer, a multiverse, or hidden variables. It is a testable hypothesis. If experiments ever show that massive objects in superposition collapse faster than standard decoherence would predict, and if that collapse scales with mass exactly as Penrose's formula suggests, it would be a paradigm-shifting discovery. The search for such effects is already underway in labs around the world, using molecules large enough to approach the threshold where gravity might kick in. So far, the results are inconclusive, but the window is narrowing. Whatever the outcome, Penrose's work forces us to confront a deep question. Is consciousness a fundamental feature of the universe, woven into the very process by which reality becomes real? Or is it a beautiful, accidental byproduct of a much simpler physical mechanism? The answer may lie in the collision of gravity and quantum mechanics, a collision that might be happening inside your own head, right now, with every thought you have. Wavefunction realism places the wave function at the center of everything, not as a mathematical shortcut but as a real, physical object. It argues that the wave function is a genuine field, just like an electromagnetic field, but one that exists in a space far stranger than the three dimensions we move through. This space is called configuration space. For a single particle, configuration space has three dimensions, the usual up, down, forward, backward, left, and right. But for two particles, it has 6 dimensions. For 100 particles, it has 300 dimensions. And for the entire universe, with all its trillions upon trillions of particles, configuration space has an unimaginably vast number of dimensions. The wave function is a field that stretches across that entire high-dimensional landscape. It does not sit in our ordinary space. It sits in a space of possibilities where every possible arrangement of every particle corresponds to a single point. When the wave function evolves according to the Schrödinger equation, it flows through this territory like a river carving new channels. The key insight is that what we perceive as our three-dimensional world is merely a thin slice of this larger object. Each particle we see is like a shadow cast by a much deeper structure. The positions of all the particles in our universe at a given moment correspond to one specific point in configuration space, the point where the wave function happens to have a particularly high amplitude. Other points in that space are equally real. They just correspond to different arrangements of matter, different histories, different universes. From this perspective, the entire multiverse is a single, unified object, a single wave function living in a single high-dimensional space. Our ordinary reality is just one low-dimensional cross-section of that object, one slice we happen to experience. This view is deeply realist. It rejects the instrumentalist idea that the wave function is only a tool for calculating probabilities. In instrumentalist interpretations like Copenhagen or QBism, the wave function is a device we use to manage uncertainty. In wave function realism, it is the fundamental substance of the cosmos. Everything else, particles, fields, space, time, emerges from its structure. This realism aligns naturally with the many worlds interpretation, where the wave function never collapses and all branches are equally real, and with the pilot wave theory, where the wave function guides particles through configuration space. Both of those interpretations treat the wave function as a real entity. Wave function realism simply takes that commitment seriously and follows it to its logical conclusion. The universe, then, is not a collection of separate objects moving through a fixed background. It is a single, gigantic wave pattern, a tapestry woven from countless threads of potential, and our everyday world is one narrow thread we happen to follow. That raises a disorienting question. If the wave function is real and lives in a space of infinite dimensions, then the true shape of the cosmos is something we can never directly see. We are like creatures living on the surface of a vast ocean, unaware of the depths below, never guessing that the ripples we feel are only the surface expression of a far more complex reality stretching into dimensions we cannot even conceive. Perhaps the deepest shift in perspective is to stop asking what reality is and start asking what we can do with it. That is the guiding insight behind quantum information theory, a view that reinterprets quantum mechanics not as a description of particles or waves, but as a theory of information processing. In this framework, the most fundamental object is not a particle or a field, but a qubit, the quantum version of a classical bit. A classical bit can be either a 0 or a 1. A qubit can be both at once, a superposition of 0 and 1, and it can also be entangled with other qubits in ways that classical bits cannot. This seemingly simple change unlocks a whole new world of possibilities. Because qubits can exist in superposition, they can represent many different numbers simultaneously. And because they can be entangled, the information they carry is not stored in any single qubit, but is distributed across the entire system. This distributed, entangled nature of quantum information is what makes phenomena like quantum teleportation possible. Teleportation does not transport matter. It transfers the exact quantum state of one qubit to another qubit far away, using entanglement as a kind of invisible bridge. The original qubit is destroyed in the process, and the distant qubit becomes an identical copy. No faster than light travel occurs, but the information is moved perfectly, as if by magic. Entanglement, in this view, is not a mysterious connection. It is a resource, a kind of fuel that can be consumed to perform tasks that are impossible with classical information alone. This idea of entanglement as a resource is the heart of the resource theory of entanglement. Physicists have learned to quantify how much entanglement a system contains, how to distill it into a purer form, and how to use it to enable quantum computing, quantum cryptography, and quantum sensing. In quantum computing, for example, a small number of entangled qubits can solve certain problems exponentially faster than any classical computer, because the qubits explore many possibilities in parallel, and entanglement allows their answers to be correlated in ways that classical bits cannot replicate. What makes quantum information theory so powerful is that it sidesteps the deep metaphysical questions that have haunted the other interpretations. It does not ask whether the wave function is real or whether the universe splits. It asks only what operations are possible, what information can be extracted, and what tasks can be performed. This is a deeply operational approach, one that treats quantum mechanics as a toolbox rather than a puzzle. It is also the foundation for the most practical applications of quantum science, the technologies that are already beginning to reshape computing, communication, and measurement. In this view, the universe is not a collection of things. It is a web of correlations, a network of information relationships, and the questions we ask shift from what is real to what can be done. That shift is not a retreat from understanding. It is an embrace of a deeper kind of knowledge, one that focuses on power and possibility rather than on a fixed picture of reality. And as we learn to manipulate this quantum information more precisely, we may discover that the ultimate limits of what we can know and do are not set by the laws of physics alone, but by the very nature of information itself. Gravity may not be a fundamental force at all. That is the bold proposal of the Dutch physicist Erik Verland, who in recent years has argued that gravity is an emergent phenomenon, much like the elastic force you feel when you stretch a rubber band. When you pull on a rubber band, you are not directly interacting with a fundamental force of rubber. Instead, you are feeling the collective effect of countless polymer chains being stretched and reoriented, each one fighting to return to its most disordered, most probable state. The elasticity you experience is a statistical effect, a consequence of entropy. Verland realized that gravity might be exactly the same kind of entropic force, arising not from a fundamental particle or field, but from the microscopic behavior of quantum degrees of freedom, the tiny bits of information that make up spacetime at the smallest scales. To understand how this works, we need to revisit the holographic principle from earlier in our journey. That principle tells us that the information content of a region of space is encoded on its boundary, a two-dimensional surface that acts like a cosmic hard drive. Verland took this idea one step further. He imagined that this holographic screen is not just a storage device but also a thermodynamic system, one that has a temperature and an entropy. When a particle approaches such a screen, the amount of information on the screen changes. The system then tries to maximize its entropy, and that tendency produces a force on the particle, pulling it toward the screen. That force, Verland argued, is what we call gravity. From this perspective, gravity is not a mysterious action at a distance. It is a statistical push, a macroscopic effect of microscopic information rearranging itself. This picture has remarkable consequences. It suggests that spacetime itself is not a fundamental stage on which the universe plays out. It is an emergent property, a kind of fluid that arises from the underlying quantum information fabric. Just as the smooth surface of a lake emerges from the dance of countless water molecules, the curved geometry of Einstein's general relativity emerges from the thermodynamics of quantum bits. The equations of gravity, including Newton's inverse square law and Einstein's field equations, can be derived from simple thermodynamic principles without ever assuming gravity as a starting point. This is a radical shift. It means that to find a theory of quantum gravity, we may not need to quantize the gravitational field in the traditional way. Instead, we might need to understand the thermodynamics of quantum information, the behavior of entanglement and entropy on holographic screens. The search for a unified theory becomes a search for the statistical laws of the universe's most basic code. If Verland is right, then the force that holds you to your chair, that keeps planets in orbit, and that shapes the largest structures in the cosmos is not a cosmic command carved into the fabric of reality. It is an aftereffect, a shadow cast by a deeper, more fundamental world of pure information, and that raises a disorienting question. If gravity can emerge from something simpler, what else that we call fundamental might also be a beautiful illusion. John Wheeler proposed that the universe requires observers to exist, that the past itself is not fixed until someone looks back at it. He called this the participatory anthropic principle, and it is one of the most mind-bending ideas to emerge from quantum theory. Wheeler imagined the cosmos as a giant self-excited circuit. The universe gives rise to observers, and those observers, through their acts of measurement, complete a loop that brings the universe into being. In his view, the past does not exist independently. It is not a solid, finished timeline waiting to be discovered. Instead, the past is a kind of potential that becomes actual only when it is observed in the present. This sounds like science fiction, but Wheeler built his argument on real experiments. The most famous is the delayed choice experiment, a thought experiment that was later realized in the lab. In this setup, a particle is sent through a beam splitter, and a detector can be placed either to measure which path the particle took or to let it interfere with itself. The key twist is that the choice of which measurement to perform is made after the particle has already started its journey. In the quantum eraser version, the experiment is even more precise. The particle encounters a crystal that creates two entangled photons. One goes straight to a detector and the other is sent through a maze of beam splitters. By choosing how to handle the second photon, an experimenter can later decide whether to erase the which path information or to preserve it. And the stunning result is that the pattern of detections for the first photon seems to depend on a decision made after that photon already arrived. It is as if the past is being retroactively shaped by a choice made in the future. Wheeler interpreted these experiments as evidence that the universe is not a machine running on a fixed timeline. It is a feedback loop. An act of observation in the present reaches backward in time and helps determine what must have been true in the past. This is very different from the weaker anthropic principle, which simply says that the conditions of the universe must be compatible with the existence of observers. That weaker idea is a logical observation, not a causal claim. It says that if the universe were different, we would not be here to notice, but Wheeler went much further. He argued that observers are not just a consequence of a pre-existing universe. They are a necessary ingredient for that universe to have a definite past at all. Without observers, the universe would remain a ghostly collection of quantum possibilities, unresolved, unactualized. This places consciousness at a foundational level, woven into the very structure of space and time. It is a deeply humbling vision. The act of looking, of asking a question, of making a measurement becomes a cosmic act of creation. Every time you open your eyes, you are participating in the birth of reality, not at the beginning, but right now, shaping what came before. And that raises a dizzying thought. If this participatory loop is real, then the entire history of the universe, the birth of stars, the formation of galaxies, the evolution of life, all of it may depend, in some subtle way, on the observers that exist today. We are not spectators watching a show that already happened. We are co-authors of a story that is still being written, with the pen held in the present, reaching back across the ages. QBism and relational quantum mechanics share a deep connection, one that draws them together into a single, coherent perspective. Both interpretations begin with the same radical insight. that the quantum state is not a description of an objective universe floating out there, independent of any observer. Instead, it is a tool, a model, that an agent builds from their own experiences and interactions. QBism says that the wave function is a personal Bayesian probability assignment, a measure of your own expectations given what you have seen. Relational quantum mechanics says that any property of a system exists only relative to another system, that there is no absolute state of the world, only states defined by relationships. Combine these two ideas and you get a picture where each observer, each agent, constructs their own Bayesian model of the world based on the relational facts they have gathered. And reality, in this view, is not a single monolithic story. It is the collection of all these consistent accounts, all these personal models, each valid from its own perspective. This is a kind of perspectival realism. It accepts that there are many true descriptions of the same underlying events, and that no one description is privileged over the others. A famous paradox called Wigner's friend illustrates the power of this approach. In that thought experiment, one observer measures a quantum system and becomes certain of the outcome. Then a second observer, Wigner, describes the first observer plus the system as a single quantum state, still in superposition. The two observers seem to disagree. But in the combined QBism relational view, there is no contradiction. Each observer has their own Bayesian model, built from their own relational interactions. Wigner's friend has a definite fact relative to himself. Wigner has a different set of facts relative to himself. Both are correct from their own standpoints, and there is no need for a universal super-observer to reconcile them. This approach resonates with certain currents in postmodern thought, which emphasize that knowledge is always situated, always shaped by the perspective of the knower. But it does not fall into pure relativism. The Bayesian rules for updating beliefs are universal. The relational facts are objective constraints on what can be true for any given agent. The world is not a free-for-all. It is a web of mutually consistent perspectives, each anchored by the same underlying interactions. In this synthesis, the universe becomes a community of observers, each carrying their own quantum map, each navigating a shared landscape. And the mystery of reality is not that there is a single hidden truth waiting to be uncovered. It is that the truth is distributed, relational, and personal, yet still coherent enough to let us communicate, predict, and build the technologies that shape our lives. The continuous spontaneous localization model, or CSL for short, takes the idea of objective collapse and turns it into a smooth, ongoing process. Unlike the Gerardi-Rimini-Weber model where collapses happen in sudden, discrete hits, CSL imagines that the wave function is constantly being nudged by a random, diffuse field that acts everywhere all the time. This field is stochastic, meaning it fluctuates randomly, and it couples directly to the density of matter. Wherever matter is denser, the collapse effect is stronger. For a single particle floating in empty space, the nudges are so weak and so rare that the wave function spreads out freely, obeying the Schrödinger equation for long periods. But for a macroscopic object containing trillions of atoms, the combined effect of all those nudges becomes overwhelming. The wave function of that object gets pinned down almost instantly, forced into a definite location in space. Think of it like a crowd of people standing in a field. If everyone is spread far apart, a gentle breeze barely moves anyone. But if the crowd is packed tight, the same breeze pushes the whole mass together, locking everyone into a small area. In CSL, the breeze is the random field, and the crowd density determines how quickly the wave function collapses. This model has a major advantage over GRW. In GRW, each particle experiences a spontaneous hit only once every 100 million years on average, which is extremely rare. That rarity means that for a small group of particles, say a few hundred atoms, the collapse rate is still very slow. Experiments that place such small clusters into superpositions should therefore see them persist for measurable times. just as standard quantum mechanics predicts. CSL, on the other hand, has a parameter called the collapse rate that can be tuned. The rate depends on the mass of the object, not just the number of particles. This mass dependence means that even a relatively small molecule might experience collapse faster than GRW would suggest if the CSL parameters are set to certain values. And that is the key that makes CSL testable. Because the collapse is continuous and depends on mass, it produces tiny but measurable side effects. One of the most promising predictions is that the random nudges will cause charged particles to emit X-rays. Normally, a charged particle in a stable orbit does not radiate, but if it is being jostled by the CSL field, it will accelerate slightly and emit a faint glow of X-ray photons. These photons would be scattered throughout the universe, creating a background signal that we could detect. Several experiments have already searched for this anomalous X-ray emission using detectors on balloons and satellites. So far, no signal has been found which places strict limits on the strength of the CSL field. These limits are getting tighter every year, squeezing the allowed parameter space of the model into a smaller and smaller corner. Another testing ground is matter-wave interferometry. In these experiments, scientists send large molecules through a series of gratings, creating an interference pattern that reveals their quantum wave nature. If CSL is real, the interference pattern should become weaker when the molecules are larger or when the experiment takes longer, because the collapse process progressively suppresses the quantum coherence. Researchers have already pushed these interferometry experiments to molecules with hundreds of atoms, and they have seen no deviation from standard quantum predictions. This means that any CSL collapse must be extremely weak at those mass scales, or must kick in only for much larger objects. But the beauty of CSL is that it makes concrete numerical predictions. It is not a vague philosophical proposal. It gives experimentalists a target, a set of parameters to measure and exclude. This places it in a rare and powerful category. It is one of the few interpretations of quantum mechanics that can be falsified by experiment. If future experiments detect a faint X-ray background that matches the CSL prediction, or if matter-wave interference disappears at a specific mass threshold, it would be a direct sign that wavefunction collapse is a real, physical process happening continuously in the background. And if such a signal is never found, the theory will eventually be ruled out. In either case, science moves forward. That is a rare gift. Most interpretations, like many worlds or Copenhagen, are designed to be immune to experimental tests. They explain all possible outcomes without ever telling you what to look for. CSL does the opposite. It sticks its neck out, makes a bet, and waits for the experiment to deliver the verdict. And that, perhaps, is the most honest thing a theory can do. Roger Penrose, the architect behind the gravitational collapse theory of consciousness, has another equally ambitious vision for reality. It is called twistor theory, and it attempts to rebuild the entire geometry of space and time from scratch. Instead of starting with points in space and moments in time, Penrose proposed that the most fundamental objects are light rays. Every beam of light, every photon traveling at the cosmic speed limit, is a tiny thread in the fabric of the universe. These threads are twistors, complex mathematical entities that encode both the position and the momentum of a light ray in a single, elegant package. The central idea is stunningly simple. In standard physics, we describe events as points in a four-dimensional spacetime. A particle is located at a specific coordinates. Its motion is a curve through those coordinates, but a light ray, by its very nature, does not have a definite position. It is a line, a trajectory that stretches across space. Twistor theory does not try to force light rays into point-like boxes. It makes the line itself the primary object. Each twistor corresponds to a spinning massless particle, like a photon or a neutrino, and the geometry of spacetime emerges from the relationships between these twistors. When two light rays cross, they define an event. When many twistors are arranged in a certain pattern, they produce the curved spacetime we experience as gravity. This is a radical departure from the standard picture. Instead of thinking of particles as tiny balls moving through a pre-existing arena, twistor theory sees the arena itself as a secondary structure, a kind of hologram projected from the dance of light rays. One of its earliest successes came in the description of massless particles. In the 1970s, Penrose showed that the equations governing these particles become incredibly simple when expressed in twistor language. The wave functions for photons and neutrinos take on a clean, almost geometric form that reveals hidden symmetries. This simplicity hinted that twistor theory was not just a mathematical trick, but a window into a deeper structure. In the late 1980s and 1990s, twistor theory experienced a revival when physicists discovered that it could be used to calculate scattering amplitudes, the probabilities that particles will bounce off each other in certain ways, much more efficiently than traditional methods. These calculations, which would have taken pages of algebra using Feynman diagrams, could be reduced to a few lines of twistor geometry. The most dramatic development came in the early 2000s when a new formulation called twistor string theory emerged. This approach merged the ideas of twistor theory with the framework of string theory, creating a powerful toolkit for computing the probabilities of particle interactions in supersymmetric quantum field theories. Suddenly, twistor theory was no longer just a philosophical proposal. It was a practical computational engine, producing results that matched experiments with stunning accuracy. Yet, despite these successes, twistor theory remains a work in progress. It has not yet produced a complete, testable theory of quantum gravity. The geometry of twistors works beautifully for massless particles, but it struggles to incorporate mass. Massive particles like electrons and protons travel slower than light and have a more complex relationship with space and time. Researchers have found ways to include them, but the mathematics becomes far less elegant. The Holy Grail would be a twistor formulation of general relativity that reproduces Einstein's equations in all their glory. Progress has been made, but the full unification remains elusive. What makes twistor theory so compelling is the way it changes our picture of reality. In standard quantum mechanics, a particle is a point with a wave function that spreads out. In twistor theory, a particle is a configuration of light rays, a twist of geometry in a higher dimensional space. The world we see, with its solid objects and smooth curves, is a projection of this deeper, more vibrant structure. And that vision, even if incomplete, reshapes how we think about the ultimate nature of the cosmos. The universal wave function requires nothing else to describe reality. In its modern form, the many worlds interpretation is stripped down to a single, deterministic equation. The Schrödinger equation governs the entire wave function of the cosmos, from the smallest particle to the largest galaxy, without any collapse, without any observer, without any special intervention. This wave function evolves smoothly, predicting every possible outcome of every quantum event as a branching pattern that spreads like the roots of a vast cosmic tree. The key ingredient that makes this picture work is decoherence. When a quantum system interacts with its environment, the wave function splits into multiple branches that no longer interfere with one another. Each branch becomes effectively isolated, evolving on its own as a self-contained reality. There is no mysterious act of measurement that forces a choice. The branching is a natural, physical process that happens automatically whenever information spreads into the surrounding environment. From the inside of any one branch, the world appears classical and definite, and we never notice the other branches because they are decohered, disconnected, and forever inaccessible. This raises a deep puzzle. If every outcome occurs in some branch, why do we perceive probabilities at all? Why does an outcome with a 90% quantum amplitude feel more likely than one with 10%? The answer lies in a mathematical property called the measure of branches. The wave function assigns a weight or amplitude to each branch. The Born rule, which in standard quantum mechanics is a separate postulate about the probability of measurement outcomes, emerges naturally from the structure of the wave function itself when you consider the distribution of experiences across all branches. An observer in a branch with a larger amplitude is, in a precise sense, more typical, more representative of the whole ensemble. The feeling of probability is not a feature of the universe but a feature of your own perspective, your own location among the infinite branches. This is a deeply elegant solution. It removes the need for any extra postulates beyond the Schrödinger equation and the universal wave function. There is no collapse, no hidden variables, no consciousness, no special role for measurement. The entire theory is contained in the wave function and its deterministic evolution. Despite its strangeness, despite the dizzying image of countless realities unfolding in parallel, many physicists consider the many worlds interpretation the simplest, most mathematically parsimonious account of quantum mechanics. It asks us to accept only what the equations already say and to let go of the human desire for a single, unique story. The universe, in this view, is not a single narrative but an unbounded library, and we are characters in just one of its infinite volumes. We have traveled through a landscape of ideas more diverse and strange than any fiction could invent, from pilot waves that guide particles along hidden trajectories to consciousness itself reaching back through time to shape the past. Each of these 30 theories offers a different answer to the same question: what is really happening when a quantum measurement occurs? Yet for all their brilliance, not a single one has been proven definitively. The debate remains open, and that openness is not a weakness of science but a testament to how deeply quantum mechanics challenges the very foundations of what we once thought we knew about reality. Every interpretation forces us to give up some treasured intuition, whether it is locality, causality, determinism, or the simple idea that the world exists independently of being observed. The fact that brilliant minds can disagree so fundamentally about the same set of equations tells us something profound about the universe and about ourselves. We are beings who crave a single story, but the quantum realm seems to offer many, all equally consistent with the data. So now the question turns back to you. Which of these visions resonates most with your own sense of how the world should be? Do you find comfort in the hidden clockwork of Bohmian mechanics, or do you lean toward the radical democracy of Everett's many worlds? Perhaps you are drawn to the quiet pragmatism of QBism or the time-bending handshake of the transactional interpretation. There is no right answer, only the endless invitation to wonder. If this journey has sparked something in you, hit the like button to help others find this exploration, and subscribe so you do not miss the next deep dive into the mysteries that shape our cosmos. And most importantly, drop a comment with your own favorite interpretation. Tell us which theory you think comes closest to the truth and why. The conversation does not end here. It continues in the space between your thoughts and the words you share.